Hello students, this is second video for assignment 1. In previous video we had these two topics, wavefront, types of wavefront and Huygens principle. In this video we will see how to explain the phenomena of reflection using Huygens principle, concept of wavefront, and refraction also will discuss. We know that if we consider a mirror and if we allow a light ray to fall on it, where the light will go? So we say that draw normal to the surface, and if angle of incidence is theta, on the other side of normal at same angle theta, the reflected ray will go. So this suggests that angle of incidence I is equal to angle of reflection R. But we have accepted this rule so far. So today, with the help of wavefront concept, we will try to prove that angle of incidence and angle of reflection both are same. So let us consider a reflecting surface. Say PQ, and let us assume that there is a wavefront AB is approaching our reflecting surface PQ. So this is the reflecting surface, and AB is a wavefront. What do you mean by wavefront AB? You should understand that there are so many waves, and AB is a surface which is passing through points oscillating in same phase. Okay, but it is basically bunch of waves. So at some time t, if you extend this, you realize that at some time A will reach here and B will be at some distance from Q. Okay, and we, according to Huygens principle, now we allow that all the points on AB will start emitting secondary waves, and let us consider that time t is 0 when we consider all the points as source of secondary waves. So our time starts from that moment, and then when the secondary waves from B will reach uh, say B prime point on the mirror, on the reflecting surface, during this time the waves of A will have same distance traveled. So how do we explain that? So I would say that let the distance be B prime be velocity into time. There must be some velocity of these waves, and let the time taken be t. So all the waves of A, all the secondary waves of A will have same distance Vt traveled in that time. Why so? Because these waves are traveling in say medium of air, these waves are also traveling in the same medium. So distance traveled has to be same. Now not only that, if you consider some point say here or here or here, you will get similar uh, distance traveled, and then if I join the tangents to this secondary wavelets, this is secondary wavelet of B, this circle is secondary wavelet of A. So if I join tangent to this, I get secondary surface. Let me call it A prime, and let this be B prime. So A prime, B prime is secondary surface, and this being tangent has to be 90 degrees. So now we are talking about two triangles. Which two triangles we are talking about? A, B, and B prime. This is 90 degree. Why it is 90 degree? Because AB is wavefront and BB prime is direction of wave propagation. So it has to be 90, distance is Vt. And then we have one more surface. which is like this. Which surface I am talking about? I am talking about A prime and B prime. Now, actually this is tangent, so this angle has to be 90 degree, and A prime is distance traveled by secondary waves from A, so it has to be Vt. So now look at these two triangles. Now I should be able to say that in triangle A B B prime and in triangle A prime B prime, measure angle A B B prime is 90 degree, and so as measure angle A prime B prime, this is 1 point. In both triangles we have A B prime common, isn't it? Moreover, A prime is equal to B prime is equal to Vt. So I can say that these two triangles have similarity. And now AB is primary wavefront, so this angle is angle of incidence for primary wavefront. A prime B prime is wavefront going away from the surface, so this is reflecting angle, angle of reflection you may say. And as the similarity is proven, I can say that angle BA B prime should be equal to angle A prime B prime A. It means that angle of incidence is equal to angle of reflection. So that is how, using the concept of wavefront, you can prove that angle of incidence is equal to angle of reflection. Let us now check how to show that angle of refraction and angle of incidence are also related by Snell's law. What is Snell's law? It says that if you consider some ray which is incident at say some angle theta 1 from medium of refractive index eta 1, it will not go straight into the other medium. Let's say the other medium is having refractive index theta 2. Instead of going straight, this ray, it would have traveled straight, but as the medium is changed, it will change its direction and it will bend towards normal. What is the condition? Condition is eta 2 is greater than eta 1. In that case, it will bend towards normal, and then there is some relation between theta 1 and theta 2. What is the relation? Relation is eta 1 sine theta 1 is equal to eta 2 sine theta 2. And if I denote this with I, if I denote this with R, and we know that eta is C by V, so I can write this as C by V1 sine I is equal to C by V2 sine R. So this is the law of refraction which we are familiar with, and we'll try to prove this. Again, so far we are not given proof of this equation, we are asked to accept it. Today we will try to prove that there is some relation between I and R, angle of incidence and angle of refraction, and that can be derived, that can be explained. So let us try to explain this. Again, I will consider the same surface PQ, but this time this PQ is not reflecting surface. In fact, it is a surface which is separating two media. Say one is having refractive index eta 1, other one is having refractive index eta 2, and there is a wavefront approaching it. I will consider it AB again. So let A point be touching the surface at time t equal to 0. At that time, B is at some distance. So by the time secondary waves of B reach the surface, say at B prime, what secondary waves of A must be doing? When secondary waves of B are traveling at speed v, and hence Bb prime is Vt, at that time the secondary waves of A must be traveling but in other medium. See, now medium is changed, and because of that the distance traveled will also not be same. So let us consider this blue line as the distance traveled by secondary waves of A. So now if I assume that secondary waves of A have reached say point A prime, then A prime would be, let it be V2t, let me call it V1t. So what is A prime? Distance traveled by secondary waves of A in medium of refractive index eta 2. What is BB prime? Distance traveled by secondary waves from point B in medium of refractive index eta 1, and V1t is not equal to V2t unlike previous case, but then Huygens principle is still applicable. Again, if I join A prime and B, again I have two triangles. This has to be right angle because tangent and radius. This has to be right angle because wave is propagating perpendicular to the wavefront. So again, uh, this has to be angle of incidence, and let this be angle of refraction. So two triangles once again. Which two triangles now we have? The first triangle is A B B prime. This is 90-degree angle. This angle is I, and this side is V1t. Second triangle is A B prime. This is 90-degree, and this side is V2t, and this angle is R. So these two triangles we have. So if I take, let me consider that in triangle A B B prime, sine of I, if I take, what is sine of I? It is opposite by hypotenuse. So it is BB prime upon AB prime, that is V1t by AB prime. Similarly, in the other triangle, A, this is A prime, A prime, B prime, if I check sine of R, look at this, what is opposite side of R? It is A prime. So A prime upon hypotenuse, which is common in both AB prime, so it is V2t by AB prime. So if I make AB prime subject of formula here, what it is? V1t upon sine I, and similarly make AB prime subject of formula in second equation, what you will get? V2t by sine of R. It means that sine R by V2 is equal to sine I by V1, or else I can say C by V1 sine of I is equal to C by V2 sine of R. But what is C by V? It is eta. So eta 1 sine I is equal to eta 2 sine R, and that is nothing but Snell's law of refraction. So this is how we can prove Snell's law with the help of concept of wavefront. And that was the topic of this video. Thank you.